We, the students of grade 12D of Greenfingers Global School Kharghar, here present the Physics Art Integration Project. When we look at this image, it reminds us of a great scientist, Sir Isaac Newton, who is known all over the world for his most important discovery, which made the core of physics even more stronger. And this discovery is none other than gravity. Every object that has mass exerts a gravitational pull or force on every other mass. The strength of this pull depends on the masses of objects at play. Gravity is what keeps the planets in orbit around the sun and the moon around the earth. Hence we define gravity as the force that attracts a body towards the center of the earth or towards any other physical body having mass.
In Newton's law of gravitation, the force of attraction between any two bodies is gravitation. If one of the bodies is Earth, then gravitation is called gravity. Hence, gravity is the force by which Earth attracts a body towards its center. Acceleration due to gravity is the acceleration gained by an object due to gravitational force. The standard value of g on the surface of the Earth at sea level is 9.8 meter per second. However, any value of g measured at a given location will differ from the g value calculated. This is due to three reasons. First, Earth's mass is not distributed uniformly. Second, Earth is not a perfect sphere. Third, Earth rotates. Acceleration due to gravity. We can consider a point mass n at a height h above the surface of the Earth as shown. The radius of the Earth is denoted by re. Since this point is outside the Earth, its distance from the center of the Earth is denoted by h. Hence we get the given formula. Observing the above formula, we can say that the value of g decreases with increase in height of an object, and the value of g becomes 0 at infinite distance from the Earth. Acceleration due to depth. Assuming that the density of the Earth remains same throughout the volume, we can consider a point of mass n at a depth d below the surface of the Earth. So the distance from the center of the Earth is r minus d. The Earth can be thought of as a composed of a smaller sphere of radius r minus d and thickness d. Hence the given formula can be derived. The relation clearly shows that with an increase in depth, the acceleration due to gravity decreases.
Kepler's law of planetary motion. Kepler described the law of planets around the sun through three laws. The first law states that all planets revolve around the sun in elliptical orbits having the sun at one of the foci. Kepler's second law states the radius vector drawn from the sun to the planet sweeps out equal area in equal intervals of time. The proof of this is that the orbit is not circular. Thus, the planet's kinetic energy is not constant in its path. The point at which the planet is close to the sun is known as perihelion, and the point at which the planet is further from the sun is known as aphelion. It has more kinetic energy near perihelion and less kinetic energy near aphelion, implies more speed at perihelion and less speed at aphelion. According to Kepler's third law, known as law of periods, the square of the time period of revolution of a planet around the sun in an elliptical orbit is directly proportional to the cube of its semi-major axis. The effect of Moon's gravitational pull on Earth. Gravity is one major force that creates tides. In 1687, Sir Isaac Newton explained that the Moon's gravitational force on Earth causes ocean tides. This happens because as the Moon's gravity tugs at Earth, it shifts Earth's mass, distorting its shape ever so slightly into that of a football, elongated at the equator and shortened at the poles. When the Moon's gravity pulls at the Earth, the water doesn't float outward. It just gets pushed and squeezed around on the globe, directed by both gravitational pull and other forces, until it ultimately ends up bulging out on the side closest to the Moon and the side farthest away. As Earth rotates within this layer of water, its land masses pass through the two bulges. These bulges are Earth's high tides. Most shorelines experience 2 high and low tides per day. One high tide to high tide takes a little over 12 hours. The Moon's gravity affects the entire Earth, pulling at every point on our planet. The strongest pull occurs on the points closest to the moon and the weakest on the points farthest away. But every bit of water is affected. However, it is difficult to predict the tides just by following the path of the moon, as the moon is orbiting in the same direction as the earth rotates. It takes extra time for any point on our planet to rotate and end up exactly below the moon. This means that the high tide bulges are never directly lined up with the moon, but a little behind it.
Its shape is rather classified as spheroid shape. By this, we come to the observation. The radius at the equatorial region is greater than that of at the pole. The difference between radius of equator and radius at the poles is of 21 kilometers. The value of acceleration due to gravity at a given location differs. This happens due to various reasons. Variation in acceleration due to gravity due to the rotation of the earth. By equating acceleration due to gravity at equator and at pole, we conclude that acceleration at pole is equal to acceleration due to gravity. By this, we can conclude that gravity at pole does not depend upon angular velocity or the rotation of the earth. Hence, rotation of the earth does not affect the acceleration due to gravity. Variation due to the shape of the earth. Since earth is not a perfect sphere, due to the differences in radiuses, the mass of the earth is not distributed equally. Since mass is inversely proportional to acceleration due to gravity, the acceleration due to gravity at poles is slightly greater than that at the equatorial axis.
Escape velocity, the minimum velocity with which a body must be projected vertically upwards in order that it may just escape the gravitational field of the earth, is called escape velocity. A body projected from the surface of the earth such with speed Ve and the binding energy of the particle on the surface being kept at rest is G capital M small m upon R. If this much energy in the form of kinetic energy is supplied to the particle, it leaves the gravitational field of the earth. So if the Ve is the escape velocity of the particle, then from the conservation of mechanical energy we have half mve square is equals to G capital M small m upon R, and finally Ve equals to under root 2gm upon R, where R is the radius of the earth and is equivalent to 6.4 into 10 raised to the power 6 meters, and putting the values of G and capital M as mass of the earth, we obtain the value of escape velocity as 11.2 km per second. This means that the minimum velocity needed to take a particle infinitely away from the earth and finally on the surface of the earth is 11.2 km per second. Orbital velocity. Orbital velocity is the speed required to put the satellite into its orbit around the earth. The necessary centripetal force required and provided by the gravitational force exerted by the earth on the satellite is thus mv0 square upon r equivalent to G capital M small m upon R square, and thus we obtain the orbital velocity equal to under root of gm upon small r. Here small r is equal to the radius of the earth plus h. Now when the orbital speed of the satellite is taken close to the surface of the earth, r smaller is approximately equivalent to the radius of the earth, and therefore v0 equals to under root gm upon capital R, and the value of orbital velocity equals to 8 km per second on the surface of the earth. A light body revolving round a heavier planet due to the gravitational attraction is called a satellite. Moon is a natural satellite of Earth. The artificial satellites of Earth includes the polar satellite and the geostationary satellite. Earth satellites are the objects which revolve around the Earth. Their motion is very similar to the motion of planets around the Sun, and hence Kepler's laws of planetary motion are equally applicable to them. In particular, their orbits around the Earth are circular or elliptic. Moon is the only natural satellite of the Earth which a near circular orbit with a time period of approximately 27.3 days, which is also roughly equal to the rotation period of Moon about its own axis. Essential conditions for satellite motion. The center of satellite's orbit should coincide with the center of Earth. Plane of the orbit of the satellite should pass through the center of Earth. It follows that a satellite can revolve round the Earth only in those circular orbits whose centers coincide with the center of Earth. Circles drawn on globe with centers coincident with Earth are known as the great circles. Therefore, a satellite revolves around the Earth along circles concentric with the great circles. Geostationary satellites and polar satellites. Geostationary satellite. It rotates in an equatorial plane. Its height from the Earth's surface is 36,000 km, which is approximately 6 times as that of the Earth's radius. Its angular velocity and time period should be same as that of the Earth. Its rotating sense should be same as that of Earth, that is west to east. Geostationary or telecommunication or parking or synchronous or satellite are always projected from the equator, for example in Singapore. Its orbit is also called the parking orbit and its orbital velocity is 3.1 km per second. Polar satellite. It is that satellite which revolves in the polar orbit around the Earth. A polar orbit is one whose angle of inclination with the equatorial plane of Earth is 90 degrees, and a satellite in polar orbit will pass over both the north and the south geographical poles once per revolution. Its time period is 100 minutes and height is between 500 km to 800 km. Polar satellites are employed to obtain the cloud images, the atmospheric data, information regarding the ozone layer in the atmosphere, and it detected the ozone hole over Antarctica, etc. Time period of a satellite is equal to 2 pi r upon V0, where V0 stands for orbital velocity. Energy of a satellite is equal to minus L square upon 2 mr square, which is the total energy. Binding energy of a satellite is equal to negative of the potential energy by 2, and work done in changing the orbit of satellite is equal to G into capital M upon small m, capital G into capital M into small m upon 2 into 1 upon R1 minus 1 upon R2.
Weightlessness is a term used to describe the sensation of a complete or near complete absence of weight. It is sensation experienced by an individual where there are no external object touching one's body. In other words, the sensation of weightlessness exists when all contact forces are removed. These sensations are common to the state of free fall. It is important to remember that weightlessness is only a sensation and not a reality corresponding to an individual who has lost weight. Weightlessness has little to do with weight and a lot to do with the presence and absence of contact forces. Astronauts orbiting the Earth often experience the sensation of weightlessness. These sensations experienced by the orbiting astronauts are the same sensations experienced by anyone who has been temporarily suspended above the seat on an amusement park ride. The causes of sensation of weightlessness in both these cases are the same.